plane parallel to xz, plane parallel to which one? xy. How about this one? Still a plane. So let's say this is the xy plane, and that line, x plus 2y equal to y 5. Right, let's say this is the plane, this is that line, then the plane x plus 2y in 3D equal to 5 is going to be this plane. It's perpendicular to that line. So the shadow of this plane on xy plane is going to be exactly that line. But when you're going to 3D, it looks like that. Make sense? Okay, so that's the difference. What else do I have? What is a normal vector to this? I'm kind of hoping these are the stuff, if you didn't know, you picked up in lab. Can somebody tell me what's the x component of the normal vector? Y? Minus 6, right? You're basically saying this normal vector is normal to the plane, right? This vector is normal to that plane, means perpendicular, orthogonal to every vector on that plane, right? So when you're doing that, you're saying that let's have an arbitrary vector on this plane. Let's say this is the plane now. Say I have this plane, and I have a point in there. Let's say x0, y0, z0 that I know. Then any arbitrary point, x and y and z, I can connect, and that makes a vector. I put all the points as position vector. I'm sorry. Let's make them into vector points. Now, this vector is x minus x0, y minus y0, and z minus z0. If I have a normal vector, n, n1, n2, n3, normal to this plane, again, x, y, z was arbitrary. x0, y0, z0 was a point on the plane. And I formed with these 2 points, arbitrary point and the anchor point. I made a vector. The normal vector should be orthogonal to that. Therefore, this dot product is going to be 0. Therefore, you know when I'm multiplying n1x plus n2y plus n3z is going to appear. And then on the other side, if you do the dot product, you will get n1x0 plus n2y0 plus n3z0. That's the gist of what you learn in the lab. I thought maybe I should do a little bit so you can remember. Make sense? If I multiply this by that and take the negative ones to the other side, you get exactly this formula, which is know the normal vector, then plug in the point and get the other side. That's another way of thinking about it. And I think in the lab, they talk about the fact that when you're talking about planes, it's a bunch of planes in a 3D space. You can think about it as solving system of equations in 3 variables. That's something that you can think about when you're intersecting planes in 3 dimensions. We're good with this. Anybody has any questions on equations of planes? One thing I want to ask, what does it mean to be an equation of a plane? What happens if what does it mean like what makes sense when I have an equation of a plane. So let's say you give me a point in a plane. If I plug it into the equation of the plane, it should satisfy the equation of the plane. Now another thing. Let's say the equation of the plane is like this, and it has x and y and z. You give me any of these two values for any of these two, I should be able to use this to find the third one. You can give me y and z, and then I should produce an x for you. And that means that that x that I produce with the two values that you gave me make a point on that plane. Fair game? Any questions? Are we good? You guys are okay? Okay. Let's start some fun stuff. And yeah. So I'm going to talk through it a little bit so you guys know the context of what I'm saying, right? So what I'm doing today is a survey of quadric surfaces. Why do I need a survey of quadric surfaces? Some of quadric surfaces are immediately used in this course. And talking about those, let me think. We used to do optimization in Calc 1. What did the graph look like when we did optimization? Had like stuff like this. There was ups and like local min, local max, and so on and so forth. Now, what are you expecting to happen? What are you expecting the graph to be in multivariable calculus? Like surfaces. And so surfaces have ups and downs. They literally have the bottom of the valley and the top of the hill, right? What is the bottom of the valley? If you look at the surface of the Earth, bottom of the valley would be a local min, top of the hill would be a local max, right? And then you have things that are equivalent to the point of inflection in 3D. So these surfaces especially, let me show you this elliptic paraboloid and hyperbolic paraboloids are going to help you understand those local mins and local maxes, basically, through Taylor series in multi-dimension, right? So those are the ones. And then there are a whole lot of other ones that we're going to discuss. We're going to discuss hyperboloids of one sheet, hyperboloids of two sheets, cones, and ellipsoid, and all the other ones. It turns out they're actually useful in parts of the physics. And you see some of these pictures. Not quite right now. We tell you how to use them if you see them. But the usage of it doesn't happen right now. Some of them we use immediately. Some of them we promise you use in future. We tell you how to manipulate them. Fair game? Okay. So that's the surfaces that we're going to learn today. Let's see. Do you guys remember conic sections? Yeah. So there was a cone, and what did you do with the conic sections? If you have a cone, you cross-section it with a plane. With different plane, it can give you different shapes. It can give you ellipses. It can give you parabolas. It can give you circle, hyperbolas, two lines, that sort of things, right? In pre-calculus, we put a lot of energy in this type, some of the standard form of the hyperbolas and ellipses. Standard form means that when you say hyperbolas, it goes like this, or it goes like this. Can you guys do the finger with the shaping? So it's either this way or this way. That's the standard form I'm talking about. Or I have an ellipses that are nice and pretty about a vertical line, or about a horizontal line, like they're symmetric. So those are the standard ones. And I gave you some example of those. Now, with quadric surfaces, we're looking at surfaces that if I cut them with this type of planes, with that type of planes, x equal to constant, y equal to constant, z equal to constant, then I get one of those, let's go back, one of the conic sections, one of the ellipses, parabolas, circles, hyperbolas, lines, points. So these are the quadric surfaces that we're talking about, basically. So a few things. In this course, I give you a long definition up there, lots and lots of variables. In this course, we are only concerned, let's write it down, quadric surfaces. We are only concerned as far as recognition goes. We use the other ones too, but as far as the recognition goes, we are only concerned with a x squared plus b y squared plus c z squared plus then lowercase x plus lowercase b y plus lowercase c z plus lowercase d equal to 0. So that's the one that we discuss. Then, and you guys can see this. Can you guys look at this and tell me, do you see the lines on that? Can you find a relationship between those curves and the planes that I gave you over there? X equal to constant, y equal to constant, z equal. It's like those planes cutting it. It's like if the planes were sharp and can cut through, right? And so what do you see? All those curves are what? What are they? The rings. What mathematical object? The curves. Ellipses, right? Ellipses, ovals, everything, everywhere I go, I cut, what do I get? Ellipses. Or circle is actually a subset of, a circle can be considered an ellipse. And so what about this one? I get parabolas, right? I see a parabola at least. What else do you see? Look at, it's a saddle. If I cut a saddle like this, what do you see? I see a little piece over here, a little piece over there. What is a little piece over here, a little piece over there? It's a hyperbola, right? And then over here you can see ellipses or circles, and then you see hyperbolas. And over there as well. So there's a little bit goes through. First of all, you kind of find what intersects, then a little bit more goes through to recognize them. Fair game? So now what I'm going to say is that I want to kind of define cross-section curves. Are in this course, when we say cross-section or cross-sectional curves, we're talking about the curves of intersection of the surface with planes x equal to constant, y equal to constant, z equal to constant. Okay? And so how do I find that? The funky business is we're trying to make sure that you know that in 3D you need one equation to give you a surface, right? But this intersection means you have one of these equations plus an equation of the surface. Therefore, if you have two equations, you get a curve instead of a surface. Does that make sense? You're going to see it in one quick minute. So in this section, to find a cross section, oh, sorry, there was no dash in here. Plug in x equal to constant or y equal to constant. I need a comma in here. Or z equal to constant in the quadric surface. Quadric surface. Fair game? All good? So now, let's talk about this first. Hold on. Okay. What is this shape in 2D? What is this shape in 2D? It's an ellipse, right? So what do you guys think this shape is in 3D? Let's think about the cross sections. What is the cross section of this surface with z equal to 5? That same ellipse, right? How about z equal to 2? Same one. Z equal to -1, the same one. So I forgot it should be in my bag, but I have to find it. Cross sections. When I say forgot, I forgot my wiki sticks. So let's say this is the shape. It has to be y direction a little more. So and let's say z-axis is going out this way. Can everybody see what I'm pointing at? So z-axis is coming out this way, right? At any plane parallel to xy plane. So what is this? What this motion is? It's a cylinder, right? It's an elliptical cylinder. So when one variable is missing, typically you see an elliptical cylinder. I'm sorry, a cylinder. Scratch the elliptical. Yes, questions? And so here are some examples. What variable is missing here? Z. Here, Z, here, Z. Look at the shape. First one was an ellipse. So the shape is a cylinder that is elliptic, right? The second one is a hyperboloid. The shape is, that again is considered, let me show you. And I forgot his name, but I'm going to ask him, or I can ask Catherine, whose name I know. What's your name? Cam, can you stand up? So here is one side. Can the back side see me? And can you make the other side of the, yes. So that's the middle one, right? And z-axis goes through this, right? And then I have that one. Thank you, Cam. So then I have the other one that is just one of these, right? It stands very straight, very homogeneous in terms of any plane that cuts it in the z direction. Now, if I want this, basically, in different directions, the missing variable is going to change. That's not quite a standard base, but look at this. X, Y, Z. What variable is missing? Y. So instead of opening up in the Z direction, it's opening up in the Y direction, right? It's going to look like this, sideways. One way is to show it that way, and one way is to show it this way. And then the same thing here, y is missing, y is missing. So let me write down one little thing. Variable z is missing. All cross sections width, that's a width. Z equal to constant are the same. So it is called what? You're saying it, say it louder. Cylinder. So that's your first one. Okay. You know the shape of one of them in 2D. That's a cylinder with that name with it. Let's take a breather. You guys are ready? Do you need 10 seconds of stretching? Yeah, 10 seconds of stretching, but what I mean is stretch or talk to your neighbor. Because sometimes talking to your neighbors clears it up. Is it sitting in well? We're good? Huh? In the back, in the back. I can't remember his name. I said I remember your name because of your hair, but I can't remember. Is it okay? Yeah, okay. You're Matilda. Slowly but surely, right? Now that I run cam, what's your name? Lane. Lane. Yeah, I know Zach and Matilda, so I know these two girls. Not much. And I know James, but not much. That's it. Okay. My friends, let's start back. Let's talk about ellipsoid. But before talking about ellipsoid, you guys tell me, what is the cross-section of this quadric surface with y equal to 1? How do I find the cross-section? Somebody yell it out loud. You plug in that. There are two equations. See that? You plug it in, but there are two equations. What are the two equations? One equation is the surface. The equation is the plane. The other equation. Both of them are surfaces. But, so how many? 38? It's going slowly. Yeah. I really don't. Do you guys know of any outlets in here by the wall? There's none, right? Sorry. Oh, this is the next one. So you plug it in. Plug in y equal to 1 in. And so you get one of the shapes. Which one are you getting? Plug in y equal to 1, what do you get? Yes, so subtract from the other side. It would be what shape? Write it down. Write that down.
I have a question. Why is my iClicker not working? Like, I can't see the question.
You tried to join earlier on. If everybody's getting this, you're plugging in what? 1 for y. What shape are you getting? Can anybody yell out this shape? But not meant to formula. What formula are you getting after plugging in y equal to 1? You're getting x squared over 9 plus z squared over 16 equal to 3/4. What shape is that? ellipse, yeah. Okay, it's getting, we're getting there, we're getting there. What shape is that? Counting down. 4, 3, 2, 1, 0. And A is correct. Huh? So this is the shape that you just did was an ellipsoid. General format of ellipsoid looks like this. What does ellipsoid look like? Can you give me a real life object that looks like that? What? Egg? Egg is good. It's a little, something synthetical. And yeah, a football looks like an ellipsoid, right? That's another one. If you're expecting me to throw a football, it's not going to happen. So what you did is actually found, yeah, I can make the gesture, I can't do. You can find cross sections over there in the, where what we did over there, we did a cross section for in direction y equal to constant. You can do it in z constant, you can do it, you either get nothing, or you get an ellipse, or you can get a point. When do I get a point? When what? Plane is tangent to the surface. So all cross sections are, the example was the iClicker. Sometimes I put the examples that are given into the iClicker so you guys do it, basically. That's something that you get used to. Sometimes you're doing the example, and the examples are in your notes anyway, because then you can actually look at the stuff that you did on iClicker on the notes. But the cross sections are in every direction, every way, every 3 ways, right? And so they are ellipses, points, or nothing. For example, x equal to A in here is going to give me 1 point, right? Because if I plug in A over A for constant A, plus y over b to power 2 plus z over c to power 2 equal to 1, this is just 1, goes away. And so I get y over b to power 2 plus z over c to power 2 equal to 0. And that only happens, this is something ponder upon. We've discussed this before, but do it on your own a little bit. 2 power 2 means it's never negative. 2 power 2 means never negative. Two things that are never negative added to be 0. What does it say about those two things? Both of them are 0. So you get y equal to z equal to 0. A solid example, I forgot to make that a solid example. I still had a and b in there. Let's say if I have x squared divided by 4 plus y squared divided by 9 plus z squared divided by 16 equal to 1, right? Z equal to negative 4, what does it give me? It gives me this cross section, which is x squared divided by 4 plus y squared divided by 9 equal to 0. Everybody agrees? The only way this can happen is if both of them are 0. So this cross section is, what was the x value? What was the y value? What is the z value? That's the cross section. It's not a curve. It's just a point. Fair game? So sometimes the intersections are just points, not quite cross-sectional curves. Okay, so that's that. So far we're good? Let's do one more, quick. So plug in what? Y equal to negative 1. Negative 1 to power 2 is 1. So you subtract. No, you don't have to subtract. What shape is that? How much time do I have? What is x to power 2? What about z? Z is to power 2. Okay. If it wasn't z, it was y, it was 2d. What shape would that be? What shape would it be if one variable is to power 2, the other variable is to power 1? Parabola? Did everybody get, do you know which way this parabola going? Do we all know which way the parabola is going? Michael, we're going to switch sides so I can see, I can go up that way also. Next time. Do we know which way the parabola is going? Let's see. It's x equal to z squared is on the other side. When you had y equal to x squared, which direction parabola opened? Opened toward which axis? Y. So it was y was of degree 1 in y direction. Now you have x of degree 1. Which direction is going to open? We're good? Did that make sense?
Would you agree with me saying it's D?
No, D, look at this. It's x is degree 1.
Yep.
Z is of degree 2.
Yep.
When you have y equal to x squared, it opens up in the y direction. If you have x equal to z squared,
Opens in the X direction?
opens in x direction. Did that make sense? Y equal to x squared. Which way does it open up? Yes. Y direction. Oh, you were pointing. When you have x equal to z squared, which way should it open up? Yes. Okay. Yes. Okay, 4, 3, 2, 1, 0. Oh, I didn't even open it to see. I'm stopping. And B is correct. Again, it's going to be x equal to 1/4 plus z squared divided by 16. It has to open in the x. The parabola opens toward the x, right? So, speaking of that, I'm going to put down, what you did is you did this one, elliptic paraboloid. Let me write down the name. This one is useful when we talk about optimization. This one and the next one are very useful for optimization directly. You can see it directly right now. We make up stories for the rest of them so you can see how you use them in the future. But we don't use them as directly as these two. These two are direct use. So it looks like z equal to, or one of the variables of degree 1. Do you see z of degree 1 only? Then you have x over a to power 2 plus y over b to power 2. The ones, if I look at the ones to power 2, are they both the same sign, SIGN? They're both the same sign. Why am I saying this? Because there's a hyperbolic paraboloid that looks like this. So the two signs are different. Or negative could be here, positive could be that. Both of these are coming in the optimization. We will see in optimization. So paraboloid goes with that one variable being of degree 1. Do you see that? One of the variables only appears in degree 1. The other do degree 2. Whether or not they're elliptic or hyperbolic depends on the sign. If I put both the other ones on one side, if the sign match or are different. Match, it would be elliptic. If they're different, it's going to be parabolic. What? Hyperbolic. Okay. So the first one looks like a bowl. It opens up to the one that is degree 1. It looks like a bowl. Okay. Can I intersect this with z equal to -1? No. What do I get? Nothing. Because these two are non-negative, it can't be equal to -1. Oh, do you see how I'm drawing the shapes? I'm the worst. I love geometry. I'm going to tell you some stories about me and geometry. We were always buddies since 2nd grade in elementary school, right? I don't like art. I really am bad at art. I like art. I'm really bad at art. So my pictures are always worse. But thankfully, I know a lot of programming. So I make up for that. So that's the best part. Art can be replaced by programming. So those are the stories. Now, can anybody tell me, when I have the ball, there's this point right here, right? So one of the cross section is going to just be a point for that one. So the cross sections for these are parabolas, cross sections, parabolas, ellipses, and could be a point. Now let's go to the next one. Do you guys need a stretch? Do you need a little bit of a... One thing that I want to say, think of a ball. Think of a ball that opens up on z-axis, right? The elliptic paraboloid is a ball. This specific one opens in the z-axis. If I have any line parallel to z-axis, how many times this line is going to intersect? 1. No matter where do I put this line, that shape is only going to intersect it once in the z direction, right? That's called the vertical line test. Do you guys remember vertical line test in pre-calculus? Yep. It's more complicated now. You have a surface, You still have, and the variable can change. But the z, imagine z is the output. So vertical line test, instead of in parallel to y-axis, is going to be in direction z. And you're, instead of checking a curve, you're checking a surface. That's something to think. It's just, whoo. I think it's fun. I don't know if you guys agree. Half the times you guys agree. Another half you guys will enjoy it later. Michael, should we switch sides? You go that way or go this way? Okay, if you have watched the pre-lecture video, this should be okay. Plug in y equal to 1. Now I have 10 minutes to explain a ton of stuff. So when you plug in y equal to 1, what do you get? So it's hyperbolic, but which one, B or C?
Right, that's one.
Okay, so if you have watched the pre-lecture video, you remember, because it's a pre-calculus problem, right? Think about it, think about it. How do I know what, so what shape are you getting? Name of the shape. Hyperbola. Does it open this way or does it open the other way? No, I'm not very, no, I'm not doing it. Which way? This way is easy. Why is this way so hard? Huh. What is the equation? Okay. Let's think about it this way. Over there, I have to be able to plug in z equal to 0 to get 2x values. Can I do that over there? Can you plug in z equal to 0? Check. Right? Y goes away. You just have to figure out, if I plug in z equal to 0, will I get 2 values for x? Yes. The other way around, if I plug in x equal to 0, do I get 2 values for z? Can everybody see that? So that's the trick. You find the the x and y intercept to figure out what the shape is. That was the video, pre-lecture video. Well, so pre-lecture videos are typically a prerequisite review.
How did you say to figure out which way it opens?
So over here, do you see that x-intercept? Do you see the x-intercept? What does x-intercept means? It means z equal to 0. Plug in z equal to 0, see if you get 2 values. Is it possible to get 2 values? And then over there, you plug in x when there are 2 z intercepts. Can I plug in x equal to 0 to get 2 values? Make sense? Oh gosh. First letter. First letter. T? T. I just asked their name. I can't remember. You're not Kyle. You're No, not Camden. What's your name? Cole. David. What's your name?
Libby.
Libby. Jack. Let me see if I can get that many. Hope I know. Vroon with a V. V. Jack. David, Cole, Vroon, Hope. We'll see. Okay, so I think we had enough time. Let's stop it. 3. No. What's the cross section? So you have x squared divided by 9 minus z squared divided by 16 equal to 3/4. So that's the cross section. Now, does this have x-intercept? How do I know? Plug in z equal to 0. Does it have x-intercept too? Does it have, the other shape has z-intercept. Does it have z-intercept? For z-intercept, I have to plug in x equal to 0. If I plug in x equal to 0, can you solve for z? No. So which one is it? What? It has x-intercept. Look at which one has x-intercept. Okay. 4, 3, 2, 1, 0. Okay, thank you. So now I briefly talk about hyperbolic paraboloid. Let's go back to this shape. Hyperbolic paraboloids. Here's the hyperbolic paraboloids. I already wrote it down. The funky part of this, in the lab, you're going to find all these cross sections to make more sense to you. When you're looking at this, can you tell in the x direction you're getting parabolas? Which direction is and people call this Pringles. Also, it means saddle, it has saddle point. So in Pringles, you get all, in x direction, you get all the parabolas downward. What about in the y direction? Parabolas upward. Here's when it gets funky. In the direction that actually vertical line test works, what? It's going to be hyperbolized. But look at that. Parabola upward, parabola downward. I did not mean to do that. Why are you giving me that? That was my error. So now here you get hyperbolas one way. As you go downward, as the cross sections going downward, you get hyperbolas the other way. And then in between, at one instant, one glorious instant, you get two lines, right? So that's the beauty of it. And so you can put these all together and get the entire shape. Let me talk about this briefly. The other shapes that I want to talk about are hyperboloids of one sheet, hyperboloids of two sheets, and cone. Hyperboloid of one sheet looks like this: x squared over a squared plus y squared over z squared minus z squared over, b squared. C squared equal to 1, right? This other one can look like that. You have everything to power 2. One of them is different from the others. And the constant is a deal maker or deal breaker. And the cone looks like this. Do I have a minute? Okay. That one looks like that. For z equal to any constant, can I find x and y? It turns out for z equal to constant, z equal to any constant, there is a cross section. Now, for For z equal to 0, cross section is a point. And the last one,